Hello. So good afternoon, everybody. My name is Luis Bru from Photonics Research Labs, and welcome back to the Peak Technology session of this Photonic Integration Week. We were going to have 4 interesting presentations on the field. So let's open the session with Timo Aalto from VTT Finland, whose presentation is called Photonics Integration on Silicon for Sensing, Imaging, and Communication. So whenever you want.
Okay, thank you. I hope you can all hear me. So I'm Timo Aalto. I lead the Photonics integration team at the VTT Technical Research Center of Finland. I'd like to thank the organizers for inviting me and you spending the afternoon here. So I first would like to thank the other people that have contributed to the results that I'm showing here. So there's a long list of people and many more that couldn't be fitted here. So a lot of people have contributed. Also, there are a lot of projects behind where the results have been obtained. So just want to acknowledge that in the beginning. Then in the actual presentation, I'm going to first show a few slides about silicon photonics in general, what it is, and then a few more slides about our 3-micron SOI technology platform at VTT. And then I go a little bit more into detail about some of the latest results we have obtained, and also sharing with you some of the kind of future prospects, what we are planning to do next. And before concluding, I say a few words about how to access the technology. So here I have a rather tight focus in the definition of the silicon photonics. So I'm going to talk about silicon waveguides used to make photonic integrated circuits on SOI wafers, so light propagating in silicon, not in silicon nitride or MEMS mirrors or something like that, on silicon wafers, which is still photonics on silicon. And the term is a little bit expanding, but here it's all about silicon waveguides. In this technology, there are actually a lot of research groups around the world. It's been already here for more than 20 years. And this slide just summarizes the open access silicon photonics foundries that are out there that offer open access to anybody to use the silicon photonics technology. And without going into the details of those, you just see that there are different platforms. There are many differences in those, so they're not identical to each other. But there's one thing that kind of differentiates us from the others, is that we are using 3-micron thick SOI, so 3-micron thick silicon waveguide layer, while the others are typically with the sub-micron thickness. And these two waveguides sizes have quite different kind of characteristics. So this is best compared by first putting them into the same scale. So this is the small sub-micron waveguide, 220 nanometers, and then the 3-micron thick waveguides. Both are single-moded, and when you compare them side by side with a bit of zooming, you see that the mode fields look quite different. So they have their pros and cons, both of them. As a really coarse rule of thumb, I would say that the low-loss passive circuits can be made more favorably with the thick silicon, while high-speed active circuits are better done with the sub-micron silicon. I go to the details later. Then about the applications, there are a lot of applications for silicon photonics. We already saw many of those today. This is one way of listing those categories here. The gray ones are the ones where we are not at VTT yet involved in applying silicon photonics. Hopefully we will be in the future, but not yet. And referring to the title of the presentation, which refers to the 3 application areas. So you can see there are multiple different sensing applications that you can use or that apply to silicon photonics, and also multiple imaging applications and multiple communication applications. So it's quite a generic technology. Then it's always good to ask why you use photonics integration. Even if you are an expert in the field, it's sometimes good to kind of check that, okay, when does it make sense to use, and maybe when not. Well, at least one area where it makes sense is when you have enough functions, many functions that you want to integrate together. So this is actually a real setup where all the components were at least sometimes used simultaneously and precisely aligned to each other. So instead of doing this, we definitely want to do the integration with the software, with the design software, just putting things together. So that makes sense. So that's a kind of a general goal, to integrate multiple functions and to get better performance. Then about 3 micron SOI technology. First of all, we have 2 waveguides, and the combination of these is really the enabler for the success. So we have a single mode rib waveguides and multi-mode strip waveguides, and we can couple light between those. There are a few things to remember about this technology. First is that we keep the light in the fundamental mode. So we can couple between those waveguides, but we keep light in the fundamental mode, which allows to make single mode systems and circuits, even if there are multi-mode waveguide parts in the middle. The second thing to remember is that we have a large waveguide core. So whenever the amount of power you can put into the waveguides is limited by the intensity of light, so the large waveguide core allows you to put more power into that. So in some applications you can put more power. We can put like a watt of optical power there in the near infrared wavelengths. Third thing is the ultra-high confinement. As you can see from the pictures here, you can see that the mode field is almost completely confined inside the silicon core. This is not what happens in the submicron waveguides. It's not what even happens in the standard single mode fiber. There is always this evanescent field and making it single moded. But in the silicon waveguides that are thick like this, the single mode condition is actually because of the shape of the waveguide, not because of the refractive index or the size or the wavelength. So that way it kind of has an ultra-high confinement inside the silicon core. And that leads to a few things. First of all, you can have an ultra-wide wavelength range. So the single mode condition is not dependent on the wavelength or the size. So it means also that the same waveguide could operate at 1.2 microns and say 3 micron wavelength. This is not possible in the conventional waveguides. Then there is very little light at the side walls of the waveguides here, and that's where the roughness is, and that's where almost all the waveguide losses come from. So that means there's very little scattering losses, and the waveguides are very low loss because of the high confinement. So we typically get 0.1 to 0.15 dB per centimeter losses. And that includes also the bends in the spirals that I use to test the losses. And then finally, there is very little light again on the side walls, also on the upper boundaries and lower boundaries, where the polarization dependency comes from, mostly, at least the geometrical birefringency. So by making rectangular, almost square waveguides, you can have totally polarization independent waveguides. So that's the third key point there. And when you compare to the 220 nanometer, you see that this is where the polarization dependency really comes from in the small waveguides. So from this, you can see also the kind of there's very little dependency of the effective index on the dimensions. So this makes these waveguides relatively insensitive to small variations in the dimensions, which is good in many cases. On the other hand, we still have to control fairly well the dimensions, and this is why. So first of all, the single mode condition depends on the relative edge depth and the width of the waveguide, not the absolute dimensions, but the relative. But if your thickness is changing with respect to the edge depth or vice versa, the single mode condition will kind of change. So that's why we also have to control both the edge depth and the thickness of the waveguide quite precisely. The other example is the directional couplers that are shown here. So we are sometimes using those, and not very often, but sometimes. And there, the coupling between the two waveguides depends very strongly on the effective edge depth between the two waveguides. And then finally, we often use these silicon pedestals, a thin layer of silicon around the strip waveguide. It has optically no meaning or functionality there, but it allows, for example, to make a heater or a contact into the silicon layer there, or it can be used as a kind of a starting point for doing epitaxial growth. So that's why we need relatively good control of the dimensions, and we are using at the moment these SOI wafers that have been trimmed with the ion beam to have the kind of a good thickness control on the SOI layer. Then the integration density is a key thing, of course, and what we have here is two approaches to solve that, so or to tackle that. And the first one is the total internal reflection mirrors that we have been having for a long time. So they are practically having negligible footprint, and a small loss. So fraction of a dB loss, 0.1 to 0.3, and half of the width of the waveguide is the radius. But we also have these Euler bends, and these were really a breakthrough that we made a few years ago. They're now quite extensively used also in other waveguide platforms. And those allow to have a basically negligible loss in a small footprint. So with the more than 10 micron bending radius or so, we cannot anymore measure the extra loss of these. And there's some hero experiment at the bottom that we did for like a 1 micron bending radius with 0.1 dB loss. But if you make it 10 micron or 20 micron, you no longer measure any losses. With those, we can make compact passive devices, and also others have designed those on our platform. So here are examples of different passive multiplexers that are at least partially using the strip waveguides to make them small. So there's array waveguide gratings, SL gratings, asymmetric Mach-Zehnder interferometers. And then, like I mentioned earlier, we sometimes use the directional coupler. With those, you can make these kind of funny-looking filters that are operating over an extremely wide wavelength range. But of course, they are sensitive to the edge depth. But the good thing is that they kind of have no wavelength limitation. You can design them very broadband if you like. Unlike, for example, with the Mach-Zehners, there is the MMI couplers if you use those, so they have a finite bandwidth. Then there's some modulators, switches, photodetectors we have done. I will not talk much about that. I mean, those are mostly kilohertz, megahertz, maybe a few gigahertz range, not faster than that. And we are working on also making faster ones, but these are for many sensing applications, so are sufficient, but not for the telecom applications, high-speed communication. For that, what we do is we hybrid integrate some high-speed devices that we get from our partners. There are some examples from an old project that we started or finished already a couple of years ago, but some kind of amplifier chips and kind of modulators, and not yet super fast modulators, but I mean these modulator chips themselves only work at 10 gigahertz, so there's no limitation when you do hybrid integration in the speed other than the other chips, what they can provide. Then a little bit more into the latest results that we have obtained. So I would start with something we got from this ongoing EU project Passion. There are a few of the Passion project members here in the event. Also, there was a Telefonica presentation. We have VLC Photonics and there was somebody from CTTC also here. There we are developing actually for optical metro networks, different technologies, but Avidity's role is mostly to develop the transmitter technology, which is targeting like multiple chips, actually going to hundreds of terabit per second in total, but this one chip there inside is supposed to have 2 terabit per second output based on 40 VCSELs that are each modulated at 50 gigabit per second. And they have been already tested and they look quite promising. Their results already at 50 gigabit per second operation. I don't go to the details of that, but what I want to show is that the integration is done with these up-reflecting mirrors. Interestingly, I mean, those work extremely well. So they are lower loss than the edge coupling from the side of the chip, which is just a kind of end facet. So it's like a less than half a dB. You have difficulty measuring it again, but they look very, very good. So this is a nice thing to couple light in and out from the 3 micron SOI waveguides. Another thing there is these multiplexers. So like I said, this multiplex is 40 different wavelengths together, and there are like a cascaded multiplexers, 2 different multiplexers to kind of do the total multiplexing, and there are some nice results from those. So these came out from the last run. These are the best multiplexers we have ever done. So the insertion loss is only about 1.6 dB. This is the average of those, and the extinction ratio is really high, 35 dB. So this is really, really nice, promising result from the 3 micron SOI multiplexing. This is the TE polarization. The TM looks almost the same. There is a very small frequency shift, and that can be kind of brought to zero if needed. But it's hard to see in a picture like this if you put the two graphs together. There will be more results about these in the Photonics West, and there is some table with the detailed results. But I again invite you to take a look at the Photonics West presentations. Then we also tried, as an alternative to the arrayed waveguide gratings, echelon gratings. So those were small, but these are even smaller, at least some of the designs. And these are cyclic. The first ones, there are two different versions of the echelon gratings, 1x5 and 1x8. So together it's again 40 channels. And with these, we got the lowest losses we have ever measured from these multiplexers. So this was kind of reaching below 1 dB loss for both polarizations. These are cyclic. It means that you have this kind of loss envelope always from 0 to 3 dB, which you cannot do anything about if you have this kind of SL or AWG. This is cyclic. So in that sense, some of the losses are higher, but at the center, it's kind of less than 1 dB. And the extinction ratio is pretty good. So those are record low losses. And then this other one, 1x5 SL grating, was not cyclic, and there all the spectra look about the same. Insertion losses, and especially the kind of the combination of the loss and the extinction ratio is quite good. And again, working fairly well for both polarizations. So kind of only small differences. And the footprint here in this SL grating is quite impressive also. It's less than 1 square millimeter, so the AWG will never be this small, at least in the 3 micron SOI technology. This is just a collection of a few previous presentations or papers about combining or using ultra-dense spirals in 3 micron SOI to do something. So this is a different kind of we have used for sensing and communication applications, even up to 1.5 meter long in a few millimeter size. So you can take a look at those in detail if you like later. Then going from the communication to the sensing, we have a couple of projects related to that. And we are working, for example, with this consortium in a mirror gas project that was developing a gas sensor for mid-infrared for these different application areas. The idea there was that we make a kind of a clever light source that is having the tunability of the output transmission rather than scanning the wavelength at the output. So then you just use a simple photodetector to measure the output, and all the intelligence is in the transmitter itself. So there was a combination of filter and kind of mid-infrared light sources. But I think the work is still kind of startly ongoing, and there are some good results there, but maybe saving those to another presentation. But in general, I would say that this 3 micron SOI platform is quite attractive also for the mid-infrared applications. We already heard some kind of light sources and detector technologies for those, also going up to like 4 micron wavelength. This platform should be perfectly low loss platform also at those wavelengths. And this waveguide mode field here that you saw, which is calculated at 1.5 micron wavelength, is almost the same if you go to 3 micron or 4 micron wavelength. It's very well confined still then. We have measured. We don't have a very good extensive measurement capabilities in the mid-infrared, so we don't know how well the waveguides actually work in the various wavelengths. But we have some discrete wavelengths. We have measured almost the same low losses as we measure at the near infrared. For example, at 3.4 micron, we measured 0.1 to 0.5 dB per centimeter losses. The absorption comes mainly from the oxide cladding, which starts to absorb light in the longer wavelengths. A good thing is that if you have a high confinement like here, there's very little light in the oxide cladding, so it will absorb very little. But of course, if you go longer into the mid-infrared, at some point it will start to absorb very much, and then you have to remove it, but you can make something, structures like this that we have also demonstrated to get rid of the oxide absorption. Then going to the imaging applications, there is optical coherence tomography that was already mentioned in the previous presentation, or earlier presentation this morning. There we have worked with two companies, Demolumics and Medlumics especially, to develop OCT technology, which is again like was stated by Lion's presentation, that it's a kind of the optical version of the ultrasound imaging. And the idea there is that we can use it for making kind of a skin cancer or skin diseases, or you can put OCT in a kind of catheter and use it for cardiology applications, kind of measuring inside the human body something, making this kind of imaging, medical imaging there. So I don't go again very much to the details, but this is one of the important applications of 3 micron SOI technology. And then the last application is the kind of LiDAR. So this is also quite attractive. What you can do with the 3 micron SOI with the high confinement, you can bring the waveguides very close to each other. You can make an optical phased array antenna that kind of allows to kind of steer the beam. And the closer the waveguides are to each other, the wider the kind of scanning range is that you can do without having the multiple interference peaks appearing. So that's what we have been looking into. And we're not done the LiDARs yet, but just to kind of studied the phased array concept so far, and actually doing that by using a tunable laser and different kind of a design that kind of so that kind of the beam is moving as a function of the wavelength. You can also do active alignment of the beam, like doing the phase modulation. This is the first demonstration that we have now just recently measured. So this shows the output simply with a kind of a microscope objective and a camera, showing how we are scanning the wavelength of the tunable laser source and the beam at the output of the phased array antenna is kind of scanning. And this is about 30-degree scanning angle between the two interference maxima. So that's quite interesting. Then finally, something about the next steps we are doing. One is the coupling light in and out. It still needs some work. We have been testing different concepts. We have some good results, like shown here. These are polished chips, so they are not so mass producible yet, but offer very low losses. But we are looking at other concepts as well. But basic idea is that we have the 3 micron SOI waveguides, maybe with some other laser chips and so on there, and standard single mode fiber, and we need something in between to couple light efficiently. So we don't want to use gratings because they have a very limited bandwidth, so something like an end-fire coupling. So these work well, but it still needs more work to make them kind of a more industrial. And then monolithic spot size conversion would be very interesting, like schematically illustrated here. And for that, we are looking, for example, to make a amorphous silicon waveguide here that is kind of locally kind of pulling the light up, and then having an inverse taper there. And nicely, if you have this small spot size locally here, so you can combine the benefits of the low loss passive platform and the high-speed kind of thin waveguide platforms, making high-speed modulators or detectors there, and maybe some evanescent coupling. Then isolator and circulator, those are the holy grail in the integrated optics. I don't see anybody demonstrated them yet really in a feasible way in integrated optics. So we have already demonstrated Faraday rotation in silicon waveguides. We have a kind of a patent pending concept of how to do this kind of a Faraday rotation, where the polarization is rotating in a magnetic field, even if you have like a spiral where the light goes back and forth. And but what is still needed is polarization beam splitters and 45-degree polarization rotators, which are not trivial to do at all in the integrated optics. 90 degrees is more easy, but 45 degrees is a little bit more challenging. So there's still some work to be done, but I'm confident that we will soon come up with an integrated isolator. Then quantum photonics is a hot topic. We are developing single photon detectors and nonlinear peaks for different quantum applications. We saw interesting applications in the beginning of the conference here in the morning. But in the interest of time, I don't go to the details there. Packaging of these peaks and also the photonics electronics integration are important things to go to industrialize the technology also. And finally, how to access the technology. So there are many ways. One is we are always having jointly funded projects like you saw, EU projects. We are happy to also listen to your suggestions on what to do together. Then we have multi-project wafer runs now 1 or 2 times a year. Now we are speeding up a little bit. It was a bit slower in the past. We were concentrating on kind of dedicated runs, but now we are also gearing up the MPW runs. There's PDKs available for that. Then contract R&D project, this is the main business we have with dedicated runs and other services. Contract manufacturing can be offered by a separate legal entity. It's VTT MEMS Fab, part of the VTT group, but they offer the contract manufacturing so you can get the research results commercialized by going to small or medium volume production in the same fab. And also some licensing opportunities are there. And the clean room facility that we are using is so-called Micronova. So it's a Finnish national research infrastructure in Espoo, next to Helsinki. We are now using 150 millimeter wafer size, but in a couple of years we will upgrade that to 200 millimeters. So we are now buying the remaining tools that don't yet support that. And it's the biggest clean room in the Northern Europe. An important aspect in going to production is the wafer level testing, which is definitely necessary in order to kind of ramp up from research to production. So just want to mention that we have that in place. And finally, to conclude, I want to say that in the electronics technology, it's a bit more kind of aligned and standardized technology. In big technology, you have multiple different platforms to choose from. And in the 3 micron SI platform, these are the benefits that we are working on and offering. So if the combination of these sounds interesting, so then you might consider looking into this platform. So thank you for your attention.
Thank you so much, Timo, for the nice presentation. There is now time for any questions from the audience.
Thank you for the nice presentation. I've got one question about the phase array demonstration you just showed. I would like to know that what was the phase tuning mechanism you were using, and at what frequency?
So this was, I think, 50 nanometer wavelength approximately. It was actually shown. I can go back to there because I think it was mentioned on the slide. If looking carefully, yeah, there is the wavelength range is here. So basically, you have a number of waveguides. You split the light from a tunable laser into a multiple of waveguides, which are having different lengths, and then you align, kind of bring them to a nice kind of waveguide array. So as a function of wavelength, they will have different phase. And this will change as a function of wavelength that we are tuning with the external tunable laser. So this was 85 nanometer wavelength tuning range to get this. But of course, by just adjusting the length of the waveguides, you can have make it as sensitive to wavelength as you like.
Yeah. And what's the frequency?
So you mean like how fast it was scanned?
Yeah.
So this was from a tunable. I think this is would expect this to be fairly like a real-time kind of a real-life, something like what you see here. It's kind of scanning. It comes from the tunable laser, how fast that is scanning. So maybe it's even slower than what is shown here. I think it probably takes several seconds to scan the whole range. Okay. But of course, that is a commercial tunable laser. It's not to be put into any commercial LiDAR system.
Okay, thank you.
Any other question? It's time for one more, maybe? No? So if there are no more questions, let's send the speaker again.